This is G481 homework booklet question 21. So we've got a diagram showing a stress against strain curve for two materials, for X and for Y. And we're asked to pick out some information about those, to tick appropriate column if the statement applies to the material. Do try and follow these instructions. If it says tick a column, if it applies, just tick. Shouldn't be any crosses around, shouldn't be any Y's ends. Just try and do what it says. Make it nice and easy for the examiner to give you the mark. Just shrink this down so we can look at the graphs at the same time as the table. And we're asked to say, so tick the appropriate column if the statement applies to the material. That does of course mean that we could have rows with no ticks, we could have columns with no ticks. Let's have a look. Material is brittle. So you should recognise a straight line that simply finishes on a stress-strain curve as a brittle material. So that in a sense is a bit of straightforward learning. The other way to think about it is, what have I got here? I've got a straight line, so that's following Hooke's law. We associate that with elastic behaviour, and we're only getting elastic behaviour before it breaks. So I'd have to say that is brittle. No indication that Y is brittle as well, so X is brittle. The material with the greater breaking stress simply is the one that goes up to a bigger stress. So that's very straightforwardly Y. The one that obeys Hooke's law, well, Hooke's law says that stress is proportional to strain, or force is proportional to extension. So that again has to be X. Incidentally, if I was asked to characterise the two graphs, X is, I hope, clearly a brittle material. Y, it's not showing typical ductile material behaviour, nor brittle material, so we'd have to make the guess that it's a polymeric material. Then if we move on to part B, Kevlar is one of the strongest man-made materials. It's used in reinforcing boat hulls, aircraft, tyres, bulletproof vests. Sudden impact causes the material to undergo plastic deformation. What's known as plastic deformation? Back to those definition cards. Back to the definition of plastic deformation. It's permanently deformed and remains deformed when the stress or the force is removed. Another way you can say that is that it does not return to its original shape, length. The word I like there actually most of all is dimensions. Does not return to the original dimensions when the stress, when the force is removed. Moving on, we get into some sums. We've got a particular type of Kevlar which has got that breaking stress and the Young modulus that we're given as well. For Kevlar thread, the cross-sectional area, that and the length of half a metre. Calculate the maximum breaking force. So I've been told a stress, so I'm straight away looking for stresses. And I'm after a force, so that's good. I'm after a breaking force, I'm going to link that to the breaking stress. So I'm thinking stress, great, force. The other bit of information on his area, hurrah, I've been given it. Even better than that, I've been given an area, not a diameter, not a dimension, so I've got the area in the most straightforward form. So starting from stress is force over area, I've got the 300 times 10 to the 9 is equal to the force I'm after divided by the 1.02 times 10 to the minus 7. And we end up with that force being the stress times the area, 309 newtons. Now the key thing here is again to read the question really, really carefully. We're asked for the maximum breaking force. We're going to do that when we've got the maximum breaking stress. If I move on, the second part of the question asks me to find the extension of the thread when I've got a different stress. Notice this is a different stress. A lot of people, when I was having a quick look over these, used the breaking stress. But it's very, very explicitly, they want to know what the extension is when we've got that stress. So I think extension, I'm thinking, okay, I'm trying to work out an extension. I've got an original length, I was given that back in the original part up here, the original length of half a metre. So if I can get to a strain, which is the equation I can think of straight away, which has got extension, if I can get to strain, then I'm going to be able to work it out. How can I get strain? Well, stress and strain are linked by the Young modulus, so I have to do a little calculation on the side here. The Young modulus is stress divided by strain. That means I can lob in the numbers for the Young modulus, lob in the value for the stress that we've got, and we end up with that strain, 9.23 times 10 to the minus 2. If What Kath's written out here is doing that with the rearranging first. Gets you to the same answer. Once I've got the strain, I can use the fact that strain is extension divided by original length. Again, I could lob in the numbers. The 9.23 times 10 to the minus 2 is the extension divided by the 0.5 metre, multiply by the 0.5, and I get down to that step there. And I get an extension of 4.6 times 10 to the minus 3 meters. 4.6 times 10 to the minus 3 meters. Okay, quite a lot of work there in that last section for 2 marks, but fair enough. Again, the thing is, you've got to be very happy very often with the stress strain young modulus questions. We are going to have multiple steps, and it did have that there. So that's G481 homework booklet question 21.